Hello. 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 Am I audible? Okay. It seems there are not many people today. So, yeah, I'll wait for 5 more minutes. Let's see how many people are joining. Then I can start. And I hope my screen is also visible. Nikhil, my screen is visible, right?
Yes, sir.
Okay, okay, fine, fine. So it will basically be a makeup class for week 4. I already actually start in last Wednesday. This Wednesday, I already took the class of week 1. I don't know whether I think Nikhil was there, but and also like week 4, we in the last Sunday, I started the PN Junction section. So I'll probably continue that only. But it's yeah. Let's wait for 2 more minutes and then I can start. Some people are yeah joining. So I'll start now. I don't think any other people are going to join. It's already 6:37. I waited. Okay. So I'll admit this person. So I hope my screen is visible to everyone. Okay. So I think last Sunday probably I discussed about little bit on the PN junction diode, and I derived the expression of the built-in potential and the depletion region width. So yeah, just a quick recap on this if some of you were not there so that you guys can follow. So I'll just draw a quick small schematic to give you a rough idea about how the PN junction. So as it is a makeup class, so I am, and not many people are there. So I'm not going to solve too many problem today, but I will just try to clear discuss some of the fundamental things and try to clear the concepts. If you guys understand that, then probably you can solve any kind of problem from this portion. Let me change the color. So let me define this side. Okay. So this will be valence band on the P side. So this is basically your depletion region. Okay. So this region is depletion region because this is the P side. This is your N side. And this is basically your depletion region. Which has a with W, and I already derived that. What will be the expression with respect to the in terms of the number density of charge carrier? But again, I will come to that short. So this is your P side conduction band. Okay, and this has, so you have to be little bit familiar with the terminologies. What I will be talking about some different terminology. So this is the band gap on the P side. So let's say my Fermi energy is tuned here. Okay, and then this is the, as a conduction band side, I'm denoting as conduction band P side ECP. Okay, and this is your Fermi energy, and this is your valence band side, so EVP. Okay, and this energy. So this is the simple energetics. I mean, you might expect some problems on the assignments on in any competitive examination with simple schematic. But this is the valence band side, and let's say this is defined as E naught. And again, on the other side, let's say in doped side, we also have the same thing. Like this is the your, let me define this one as EB, this region. This is a conduction band on the end of side. Conduction band. Okay. Then ECN is done, and then this is again EG, the band gap. This is your guys, mute yourself. If you want to ask any question, then you can unmute. This is valence band. So this is a schematic or energy band diagram. Of an open circuited PN junction. Okay. So, okay, this is done E naught, EG, and this is basically you can define the along the X direction is the distance. Okay. And this is your junction. Fine. So now the energy barrier for electrons trying to go from inside to p side is eventually from this we define the built-in potential ECP minus ECN. Okay, this is EB. So I'll do a very quick derivation on this. So already I told you what will be in terms of NC and ND. So earlier equation we already defined all these things. So ECN can be rewritten as EF plus KT. So this I derived in my earlier classes. I'm just using that, and for VP it will be EF minus KT NV by NA. Okay. Also, you can easily see from the schematic. We'll use this expression. This is also a very important expression which the earlier classes were derived, and therefore so the PB will become, so basically it's EB by E. Okay, and another expression I also use is the width of. So probably for today's class, we can mark it as equation number 1. And for width, I'm not going to derive it again. 1 second. Yeah, so to the per half. So this mark it as equation number 2. These two questions are very, very important. So you can note it down. To a little bit understand the forward and reverse biasing of the PN junction diode. So the basically the symbol is forward bias. Let's say we have a PN junction. In between, we have the depletion region that we simply highlight using a line itself. So this side is P, this side N, and then yeah. So basically, P terminal is connected to the positive electrode of the battery. This basically staying at positive, and this is the lower negative potential. So this is how we define the forward. If you see any problem with this, then understand ki, okay, this is the forward bias condition, and reverse bias is ulta. So where you have a PN junction. Now instead of positive, okay, I don't know, this making some auto correction, and then yeah. So this is negative, this side is positive. So if we draw the band diagram, let's see how it looks. So how the electric potential will be. So now,
Sir, good evening, sir.
yeah,
Sir,
tell me.
sir, for fourth week, sir. Problem
Yes,
solving
yes.
session. Oh, thank you, sir. Sir, this coming Wednesday, actually, week 6 assignment deadline, sir, actually. I have some doubts in that assignment 6, sir.
Okay, okay. What?
Actually,
Yeah, tell me.
In Tuesday also, you are taking the problem solving session, sir. But there
Yes.
is no link pasted in the PMR of Excel sheet, sir. Just
Okay,
Sunday
okay.
sessions one
Yeah, actually, I
you are
will tell
post.
you one thing. The Wednesday week one class the recording didn't get saved. I already told the NPTEL coordinator. So week one
Okay,
is already I will retake it. I mean, I will make the video by my own. Then I will like
okay.
upload it on YouTube. But for other than that, it is
Okay.
already there, no? All week five and
So that is Sunday session. Sunday 3:30 to 5:30
so
session recorded video.
which one you want actually right now? Week fourth, I'm taking it today. So week six,
Okay,
I
sir.
will take tomorrow.
Actually, oh, okay, sir. Sir, week 6, actually, in Sundays, you are taking just lecture videos only, sir. Not problems. Actually, the
No,
related
I am
problems
doing the
are
both. No, I am also doing the problem solving session, right? I am actually created some of the problems and then I'm discussing it live only. So you tell me what kind of problem solving you want. Accordingly, I will make it and tomorrow probably I'll do.
okay, sir. I have a doubt in assignment
Ye-
6, sir, actually. Uh,
Yeah.
actually,
Okay. So actually
assignment,
assignment problem directly I'm not supposed to discuss. No, that's why I didn't do that. You understand, right?
sir, I am right, sir. But I saw that instructor videos. I
Huh.
cannot get the idea from the videos.
Okay, okay.
So
So you
only,
can do one thing. If you just
okay, sir.
tell me now, or maybe you can email me that. Is that okay?
Your mail ID, sir. Sir, already,
Yeah, so
already
I'll do one thing.
the
So I can see your name. So you do one thing in Microsoft Teams. You send me a hi message, okay? And then
okay, sir.
we will find the email from itself, and then you
Okay,
send the email with all the whatever problem is there. Actually, I kept on asking my last class also. So people were not asking any questions. I mean, I told them to ask if you have some particular question. It's good that you are asking now, because in if you see
okay,
the
sir.
last classes also, I asked people. I mean, if you have some doubt, you can always tell me. I mean, you can email me also so that I can in the next class I can discuss about all these things, because I don't know no until you say all these things, right?
Sir, actually, the instructor Digpio Jai, yes.
Yeah. Yes. Yes.
So I just mailed him. Actually, I have some doubts. Clarify me like that. I send a mail.
Okay.
He replied me. I'm my three TAs only the instructor. Actually, they are only handling Arup, Sai, and Kritik only the TAs. So you can contact them like that. He sent the mail ID. I just
I don't understand.
asked,
Who is there any other PMR also for this? Because I'm the only one, I think.
sir, ARUP, Arup, Sai, Kritik.
Okay,
Three,
three
T-
TAs.
yes.
Okay, so you
Sir,
do
actually,
one
this.
thing, John. I will tell you. So you just email me, okay? I will today only
Okay.
sit with all this whatever doubts you have. It is applicable for everyone, whoever is attending the session. If you have any doubt, you email me. Okay, or
Actually,
you post in the chat box.
okay, okay, sir.
Okay,
Actually, I
so
know your name. I know your name only.
yeah,
So just the instructor, I just mailed the instructor. So
yeah.
instructor informed me to contact the three persons.
Okay, okay, okay.
So I just asked that out to the three persons. They don't do any reply from them.
Okay, it's fine.
I
I mean,
didn't
you
receive
don't
any.
have to ask. Yeah, right. So
Okay.
if you have some
But
specific,
actually,
yeah,
yes, sir. Yes, sir. Actually, the sixth assignment, 13 problems are actually,
okay.
and the delay asking actually from the given gain versus frequency plot of BJT. Find
Okay.
out the overall delay of the transistor. The similar graph is shown. They are
So,
giving the
and
magnitude
tell
and
me one
frequency
thing, from
of
where you are just assignments, it's in the course itself, right? There is a NPTEL website and you are
okay.
getting, so if you send me that, then probably I can do it. I mean, right now I have to think it, because tomorrow I'm going to take the BJT and all these things, because this is a makeup class,
Okay.
no? So I am not like discuss
Okay,
all
sir.
these things. So it's for the particularly week 4. So I'll do one thing. Tomorrow
Okay.
probably I will start that and discuss all this thing.
Okay, sir. No problem, sir.
Okay, so you do
Sir, I
one
will
thing, no? You email me, right?
contact via. Okay, sir. Sure, sir. Sure. Sir,
Yeah,
I will send the hi, sir, in chat box.
yeah, you do
I
in
need your
Teams,
reply, sir.
then you send me. I will reply, okay?
Okay, okay, okay. Thank you,
Okay,
sir.
thank you for pointing out. I will, whatever I can do, I will try to solve all these issues, okay?
Okay, sir. Okay. Thank you, sir.
Yeah, no problem.
Thank you.
Yeah. So as it is a basically makeup class, right? So that's why I'm actually, I know already the BJT portion has been discussed, but still I'm in the PN junction because it's a week 4. Yeah, so I hope it's fine.
Sir, actually, I saw your last three videos.
Yeah.
Sir, you are mentioning the basic things which is available in the lecture videos. So
Okay,
I
okay.
need which is new. Actually,
Okay, so I will
the
directly do some
assignment
problem
questions.
solving then.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay,
Related, just I'm not asking the assignment problems to do here.
okay.
Just as a sample problem or any
Okay, some
sample problem
standard
or any
sample
model
problem I
problem.
generally
Yes,
did
yes.
also in the earlier classes also. Yeah.
Yes, sir. Now I asking the delay problem. So, if you want to, you can help means just related to delay or how to measure the delay from the graph. Like that, you have to, you can solve means it will help us.
Okay, sure. I'll do that. You send me that, then I will tomorrow I will
Okay.
discuss. Okay.
Okay. Okay. Thank you, sir.
Okay,
Thank you.
fine, fine.
So
I'll do
don't.
that. Yeah,
Yes, sir. Thank you, sir.
yeah, no problem. I will come to the problem and solving after some time now. Yeah. So this is the forward bias condition, and this you can denote as electric potential. Is for the forward bias. Now let's come to the, okay, sorry, this is the PB. Again, I'll do the same thing for the reverse bias, just to give you an idea. Okay, so this is also the distance from the junction, and this is the electric potential. Sorry, this is, yeah. Now I'll come to the current voltage relationship of the PN junction. I'm taking a condition of the forward bias first. So now there are to derive the equation which is relating the current and applied voltage in a PN junction. To start with some following assumption. So the injection level of the magnetic areas is actually low. Magnetic areas we don't consider that much. The injection level is low. Then the applied voltage is completely dropped across the depletion region. So these understandings are actually very important whenever you do the problem solving. And there are other two also. There is no generation and recombination within the depletion region that you have to remember. There is no generation and recombination within the depletion region. Which of P and N regions are large compared with diffusion length? Now let consider Pn naught is basically your equilibrium concentration of the holes in the N region. Okay, the equilibrium now we are applying a forward bias which is P and potential barrier height. The potential barrier is Pb. But you are applying also forward bias of V. So now then basically your across the junction, the effective potential barrier height is reduced to Vb minus P, which I just told you in earlier cases in the forward bias. Now, according to the Boltzmann statistics, the number of the holes which is capable of crossing the barrier, which basically increases disproportionately to e to the power Ep by kT times. And now I'll write their concentration, which is at the space charge boundary at x equals to 0. And this is and if I go back to the diagram, this side is corresponds to P naught. And this is basically your Pn naught. This concentration we'd love to find. So this is the x direction. So Pn naught will be, this is e to the power Ev by kT. Now the excess concentration of the holes diffused through the N region according to this law, which will be And the excess concentration is nothing but excess concentration is nothing but Pn naught minus Pn naught. Okay, the equilibrium condition, and then the moment we apply the forward bias. Okay, so now let's say we are defining the excess concentration as the way it will diffuse along the n region is Pn prime x. Here Lp is basically you can consider as the diffusion constant for holes. The hole concentration at any distance x is already we wrote this thing Pn naught, which is e to the power EV by kt minus 1 times e to the power minus x by Lp. Now therefore the hole diffusion current density at junction, which is basically sitting at x equals to 0, at x equals to 0. Okay. So if you do the first derivative, we will get something like this. So similarly, the electrons which are crossing the junction from n side to p side, that will also give rise to this minority electron diffusion current density, which will be basically we can denote as, this has been denoted as Pn from p to n. Now from n to p, instead of dp, it will be dn. It's simple actually. This is ln now. Okay. And this Boltzmann term will be the same. It only depends on the forward bias voltage and at what temperature you are operating. Now, because of the low level injection minority drift currents, and this this minority drift can be neglected compared to the due to the diffusion, and therefore we get the total forward current density we can denote as J, which will be sum of both the sides in P 0, which is nothing but J naught. We can denote as J naught V by KT minus 1, where your J naught is one second. I think the screen. Guys, can you see my screen now? Yeah, I think there is. Now you can see, right? It
No,
got
sir.
black. Yeah.
So just black background only.
Yeah, right. Yeah. Yeah, I will email you after this, okay? I already
Okay,
got your
sir.
ID. Okay, yeah, sure.
Okay.
Yeah. I think right now it's visible, right?
Sir, visible, sir.
Okay, thank you. Yeah, so you know where you can find the expression of J naught and it has a certain dependence. So this formula is important where J naught is times this is the diffusion length. Okay, so we can mark this equation maybe earlier. I don't know, something happened. Everything got shifted for some reason. Anyway. So let's say you have a cross-sectional area now, which is A, your cross-sectional area. Cross-sectional area is A. So then you can find the current itself, the total forward bias current. So which can be defined as is J multiplied by A, and this is I naught e to the power EV by KT minus 1. When you are operating at a very high, let's say large enough compared like to the KT by E, and your fee is very high, is large, and compared to KBT by E, this KT by E, then you get something I naught e to the power EV by KT. Okay, and in a reverse bias condition, this is for forward bias. It changes exponentially. For reverse bias, PN junction, your V is negative. V is negative, and I will be your approximately minus I naught, and that is it's called the reverse saturation current. And current. If you draw the graph, it will be something like this. This then slightly increases exponentially. This on the forward bias, then we get something like this. Yeah, which is a dark current, which is we denoted as I naught. This is the forward bias. This is the reverse bias. Okay. This is the current voltage characteristics of a PN junction diode. Okay. So in practical, the silica for like silicon and germanium diodes, it's found that the forward bias current does not assume a significant value unless the forward bias exceeds a certain threshold value, which I just told you, which is can be denoted as threshold value for each of the semiconductor. Let's say threshold value, which we can consider as V gamma, called out the cutoff voltage or cut-in voltage. Okay. And this, when we are applying a forward bias, so generally it exceeds that V gamma. Okay. So when the moment it becomes equal, after that it starts conducting. So then it is related to your built-in potential of your PN junction diode. So it can be also written as NEND divided by Ni square. Okay. Now there are some typical values for V gamma is close to 0.2 to 2.3 volt for germanium, where for silicon it's slightly high. It's close to zero point 0.6 to zero point 0.7 volt for silicon. So it should like the value of the V gamma also depends on the doping concentration as well as the temperature. Okay. Now one more thing. Fine. So this is also important. Yeah, well, this expression, I'm not sure whether it has been discussed in class or not, but this expression also is important for the problem solving session. So I'm just doing it the temperature dependence of the reverse saturation current, which is I naught. Saturation current. How the I naught generally depends upon the temperature. Okay. So I naught basically can be written as a in terms of like your dp, dn, the diffusion lengths, lp, ln. Okay. And the also can be written in terms of the minority concentration on the pn naught and np naught. Okay. So these are basically this thing I naught will vary in the temperature. So now I already derived this thing, so which is I naught from the last section. Yeah, this when I was doing from here. So I naught is a function of A dp, right? dp lp nd dn ln na ni square en naught, where from the mass action law you can write this v naught, which is basically for ni square, or you can write nd pn naught in p0 na, which is also ni square. Now ni square, if you do the from the Arrhenius equation, so you will find this already we have done in the earlier classes. So it's in terms of the band gap of the semiconductor, which is TQ times e to the power minus Eg by kT. Okay, now this terms dp, dn, these are also function of temperature. Okay, so now we can write I naught equals to C naught C or with some constant, okay, proportionality constant, and then T to the power alpha e to the power minus Eg by Kt. Okay, this is the dark current expression. Now alpha depends on the material. Okay, what will be this exponent? You guys can write this expression down, how it is changing with temperature, the reverse saturation current. This is important. So alpha depends on the material.
Sir,
Yeah.
sir, I have a doubt in assignment 4.
Okay.
So actually, regarding the relations between drift current and diffusion current, sir,
Yes.
the same assignment 4, 10th question asking the forward bias. In forward bias, diffusion current in the PN junction during the forward bias is due to, okay, sir, is due to, there
Okay.
are four options like majority, like minority, like that. Actually, the lectures explains majority concentration for diffusion current,
Yeah.
minority concentration for drift current, sir.
Yes.
Majority concentration for diffusion and
Yes.
minority concentration for
Yeah.
drift.
It's a
But
combination of these two, right?
yes, sir, these combinations. But the question is diffusion current in a PN junction during forward bias is due to. Uh, I just choosing majority holes in the P side and majority electrons in the N side. But the current, actually the answer is incorrect like that says.
Is it?
And the correct answer is minority electrons in the P side and minority holes in the N side.
Okay.
Like
Can
that,
you
they are
so can you
available.
post the screenshot now on the chat box?
Yes, sir. Yes, sir.
Please
Sir,
do that. I'll
actually,
check. No,
yes,
no, plus
yes,
do
sir. I
that. No,
will.
I will check now. Yeah.
Okay, sir. Okay, sir. Okay, sir. I will do that, sir.
And tell me what are so why where you are getting this? You are saying the right answer after checking, right? The evaluation.
Okay, sir. Okay, sir. Okay, sir. I will post it, sir.
No, I
Okay, sir.
mean, if you post it now, is that fine or like I can check it and tell you?
Okay, sir. Okay, sir. Sir,
Okay.
in chat box, shall I post it, sir?
Yeah, you post it. I will check
Okay,
and
sir.
keep a note.
Okay, sir. Okay, sir.
Yeah. Yes, it is possible. I will upload today only after the class. You will find in the worksheet of that thing.
Sir, I posted, sir,
Yeah, 1 second.
that
Yeah.
question. Yes, sir.
The 10, yeah, I got the answer. Just 1 second. The diffusion current junction. It's actually due to the movement of the majority charge carrier. So holes from the p side and electrons from the inside. Yeah. So I don't know why it is saying it's incorrect. I mean, you selected the majority holes in the p side. That's the selected one, right? If I'm not wrong, that's in the gray color. First one. Nikhil, are you there?
Sir, first
Hello.
one I selected, sir.
Yeah,
A
that's what I'm
option.
saying. That's what I'm saying. You
Yes,
selected first one, right?
yes,
Yeah,
sir.
so I don't know. This should be the right answer actually. I mean, is there any
Yes,
glitch
sir.
in the
This regarding I yes, this regarding I mailed it to that, but
Yeah, I
there
think
is no reply.
it's a
That's why
system
I asked.
dependent thing. No, they have put a wrong answer in their server. That's the only thing.
Yes, sir. Sir,
Yeah.
like
So
that,
what they told?
remaining assignment two also, sir. Assignment two and assignment three also, sir. I have some wrong answers,
Okay, so
but
you
I
do one thing. No,
mentioned.
Nikhil, I will convey this to the coordinator then.
I'm John, sir. I'm not Likil.
Oh, sorry, sorry, John, sorry, I just a bit confused. Yeah. So, John, I'll do one thing. So, if you think they
Okay,
are
sir.
not, I can directly talk to the coordinator or maybe Avina ma'am that this is the problem. Some of the students, even after choosing the right answer, they are getting zero.
Yes, sir.
Okay. So,
Yes,
did
sir.
you face any other similar problem with other questions?
Yes, sir. Assignment two and three.
Assignment 2 and 3.
One
You
problem.
do one thing, no? Can you paste do the same thing here? You paste it here. I will
Okay, sir.
do
Okay.
one thing. I will take the screenshot, compile them, and today only I will send them. And maybe by Monday I will get the answer. They will reply.
Is there
Okay.
any problem? I'm posting here.
No,
Otherwise,
you
I
post it
mailed you.
here. No, it's or you can. I will do one thing. Today only after the session, I'm going to write you back to your email ID.
Okay,
Okay. Then you
okay, sir.
also attach that file in my email. That will be also fine.
Okay, sir.
So why I'm doing because
Okay.
it's also getting recorded, right? In that case I can tell them. So this is the problem. This some of the students are mentioning your portal and the
Yes.
server. The some wrong answer is getting saved. So that's why they are not getting the point. Yeah, that's why I thought. Yeah.
Yes.
Okay, I will. I
Yes,
will
sir.
tell. No problem. Thank you for pointing out. Yeah. Okay, let's come back to the. Yes, and someone was asking me in the chat box due to the network issue. I need a yeah. Already the video will be recorded and I will upload in the YouTube, so it's fine. I mean, don't worry about that. Yeah. So I was talking about the temperature dependence of this reverse saturation current. So alpha actually depends on the depend on the material. So what will be the exponent value? So particularly alpha will be 2. Let me change the color. Alpha will be 2 for germanium and alpha will be zero point 0.5 for silicon. Okay. So yeah. So also we can do one thing. And this easy. If even if for particular for material, the alpha is also constant for particular material. Once we choose it, let's say either silicon or germanium, particular material, then this term eventually becoming constant. So we can write I equals to I naught equals to rather C1 and e to the power Eg by kT. So the reverse saturation currents you can only see it depends on the temperature. And the second parameter is basically or it's a material dependent thing which is C1. So you can also see. I mean you can rewrite basically. One sec. Run. I will also talk about the rectifiers, but before that, let me solve some problems as you guys were asking. It will be better. Okay. So we'll also quickly discuss some of the, like, if in any kind of problem, let's say there is something called junction resistance, a term. This junction resistance is basically a static DC resistance. It will be simply first thing RC equals to applied bias and the current. But this you can also consider as a DC resistance. Now, in any point, if you're asked to do the at any operating point, then generally that's a dynamic resistance. You define as, one sec, R equals to del V del I or dV di at operating point of the PN junction. So for under the large enough forward bias condition, I already told you, derive the expression which is I equals to I naught, this is a reverse saturation kind, times EV by eta kt minus 1. So now I'm taking the derivative on both the sides. Give me a dynamic resistance, which is di dv, which is by eta kt I naught e to the power ev by eta kt is I plus I naught and then R equals to your dv di eta kt I
Sir,
plus.
sir,
Yeah, tell me.
sir, I posted two questions, sir. No, totally three questions. Already
Okay.
posted one, and
Okay.
second one I posted
Let me check it. Let
in
me check one
third
sec.
assignment. Third assignment, yes, third assignment. They are mentioning
Yeah.
C option. I mentioned C option,
So one
but they are
second.
telling
Question number 13, right?
yes, 13. Yes, yes, sir.
Yeah. Find the diffusion length of electron in a semiconductor lifetime. Fine. Next is carrier. Okay.
Shell.
You have chosen 25. I need to calculate. Only after that I can comment whether you did it right or not. So, you are saying ki 25 micrometer and then carrier decays linearly.
Uh, exponential.
Yeah, right. That is exponential actually. Yes. What you're saying.
Yes.
Okay, so I don't know why this thing is happening. I mean,
So
okay, let me
actually,
what? Yeah, tell me.
somewhat I refer the lecturers. I
Ah,
know this is correct answer, but why I was wrong, I don't know.
no. I am not saying you are wrong answer. I just 25 itself is 25 or 8. That's what I just asked. Okay. Maybe it's
Yes, sir.
actually 8. You understood? I mean, I need to calculate then confirm. That's why I told. Yeah. Maybe it's 8 micrometer exponentially. That's what I'm saying. There are two options, no?
Yes, sir.
You
So
didn't
actually
understand me
25
what I was saying. Yeah, it's 25 you calculated, then you are saying no.
Yes, sir.
Yes, that's what I'm saying. I don't know, no, whether you it is that's what I just told. Yeah, it's fine. I mean, I don't know why it is saying accepted answer is because and then I don't know what I'm supposed to do here. If the portal is saying this, I can only do like I can convey this to the coordinator. Okay.
Okay, sir. Okay, sir.
So that's what I can do. If later on they don't change it, then that is not in my hand. Let's see what is the second thing. Okay. Did you mention during the live classes? John, hello.
Yes, sir. Sir,
Did you mention
actually,
all this?
I just sent these screenshots
Yeah.
to Kritik. To
Who?
Kritik. Kritik.
Okay. Okay.
Yes. Which are the questions wrong? These three questions wrong. Actually, I know. Maybe
So
is
does
correct
they
or
take
wrong.
any further action based on the input from the student or not?
Okay, sir.
No, no.
Sir, I
Matlab,
just
what I'm trying to say, they later on change it or in the portal or they don't do anything. Like I mean, I can also
sir,
convey
there
this
is
to the coordinator. That's it.
no reply from the TS.
Okay.
There is no, sir, there is no reply. I just mailed uh,
Okay.
3 or 4 times already these
Okay.
questions like this. This is which is the
Okay,
correct answer.
I
Like
will
that,
do
I
one
am
thing.
asking.
John, I'll do one thing. So on Monday, so
Okay.
see, today is Saturday. Okay, I can't office hours is already not there. So I can write them to the NPTEL team. Okay. And also I
Okay.
can CC to Digvijay sir maybe in that case if they are not responding, then I'll ask them to update. Is that fine?
Okay, sir. Okay. Thank
Okay,
you,
is
sir.
there any other discrepancies or questions you find okay it's not matching with the expected answer what you are doing? Is there anything else?
Sir, another question also I posted, sir.
I saw that. So this is that's what I'm saying. This is semiconductor material has been doped with acceptor impurity. This one, no, it has contains some
Yes,
schematic ECEFEV.
yes, sir.
Yeah, so other than all these things, do you have any other thing that you found it's not
No, sir.
matching? Okay,
No.
then I will compile all these things and probably I'll write an mail to on Monday. Probably let's
Okay,
see
sir.
what they say. Okay.
Actually, totally five assignments completed, sir. Actually, totally 5 assignments completed, but in 3 assignments, I got this wrong answers.
Okay, this is probably see this is a system problem. I mean, yeah, you good that you reported. It's fine. I will check if I can. I mean, I'll try to make sure ki this thing doesn't happen in future. I mean, I will tell them ki some students are saying that repeatedly these things are happening. So yeah, I will. I'll see. I will also check ki why the other Ts are not responding to your email. Okay.
Okay, thank you, sir.
Okay. Yeah, no problem. Thanks for raising this thing.
Okay, thank you, sir.
Yeah, no problem. Can you mute yourself? Yeah, sure. Thanks. Yeah, yeah, for forward bias, then the expression for like it will become once the forward bias condition, it's I is greater than I naught. So this dynamic resistance become eta kt E but by 1 by I. Okay. There is another called term is called CT, which is you can in called as incremental capacitance. Incremental capacitance. just dq dv. Okay, this you can keep in mind. So this will try to derive what will be the expression for this dq dv. Okay, let's say sec. I'll simply write it actually. So the final expression, probably this, and you can use this thing for the exam. This will become, so there is a long derivation. I'm not going to this. This is the area. This is ND 2 epsilon VB plus mod of VA. Okay. So how the CT looks like. Then I'll come to the diode portion. Yeah. That is done. Rectify half wave and full wave is remaining. Yeah. Rectifiers. So there are two things. One is the half wave rectifier. I hope you guys are already familiar with this. I'll just quickly touch upon and do some problem solving. Full wave rectifier. Okay. For generally half wave rectifier, this is the equivalent circuit. It's the only one diode and then the resistance RF. This is the output. Current is flowing in this direction, I. And sorry, there will be a load resistance at the output where we are measuring the signal. This is the V output. So let's say my inputs are written like I naught sine omega t. So for the first cycle, it will pass through. It will allow the current to pass, and for the other half, it will block. So that is why it is half wave. And for the other half of the sinusoidal wave, it will block it. That is why it is called the half wave rectifier. This is the current expression. Is the peak of the maximum value of the load current. Load current peak value. Input voltage is Vi. So output voltage sorry is IRL. So let me draw the corresponding schematic. Plus minus 0 pi 2 pi 3 pi omega t. This is Vi. Okay, this is the current. No, so now IDC will be I by 2 pi 0 to omega t. I don't know what is happening. Only for the first step it will conduct, and zero to pi, it will be, this is the DC value. Okay. So the DC voltage that is developed across the output, across the load RL is IDC. Sorry. Right. Now, if in the problem generally you will found once you evaluate this thing, a similar condition you will see, you will be asked to find out the RMS value of the current. Okay. So it's a root means square value. Root means square. Basically, you take the mean of the square, I square d of omega t. So again for the first half, because for pi to 2 pi, condition is 0 as current is already 0. If you solve it, you will find the RMS value for this half wave rectifier condition. It will be peak value by peak value ka half. So the total input power to the rectifier circuit, P input RMS square plus RF plus RL. Now the total DC power, only the DC power supplied to the load, not for the rectifier, only to the load, PDC. That was the input. This is IDC square RL. Okay. So there is a quantity that interest to this rectification purpose is called the efficiency of rectification. How much efficiently it can rectify a AC signal. Efficiency of rectifier This is denoted as eta. As eta. It basically measure the fraction of the total input power, which is converted into the DC power. Okay. So eta is basically P DC by P input times 100%. Okay. This is square RL, I square RMS, RF plus RL times 100%. So if you already, I derived that, if you substitute the expression of the IC, will get a final expression, which is, you also try to solve this thing by yourself once. It will be a fraction of this two, so the ratio of these two resistances, and then 100%. Roughly, it will be 40.6 divided by 1 plus RF by RL percent. Okay. So the maximal theoretical efficiency is 40.6 when it's basically eta max is close to 40.6%, where your RL is greater than RF. This load resistance is greater than RF. Okay. There is something called ripple factor also. I'll ripple factor. Efficiencies part is done. Now we'll come to the ripple factor. So let's say basically your output of the rectifier is kind of unidirectional, but so it has a pulse, right? So the ultimate purpose to produce a smooth DC is not perfectly achieved. So in fact, by making a Fourier analysis of the output wave form, we can basically show the output contains the DC as well as a large number of harmonic components, which I mean basically you can write the I first y naught plus I by y plus it's basically the Fourier analysis of the output minus, let's say, the second harmonic, the cos 2 omega t, and then by 15 pi cos 4 omega t, and goes on. So ripple factor is basically, it's a measure of this fluctuating component, and hence the lack of the smoothness you can, which is generally expressed by gamma. So the gamma is defined as the RMS value of the AC component of load current divided by the DC value of the load current or voltage maybe. Okay. To find this here, we have to first write. This is the definition of the ripple factor. Okay. So it's IDC plus IAC. Now IC, this is a total one. Okay. IC is total minus the DC component. Here IC is basically your represents the RMS value of the, no, sorry, the AC components of the load current. Now if we try to find out the RMS of IAC is given by Therefore, the gamma is I prime RMS by IDC. So we can also write like IRMS IDC square minus 1. So this already you know from the old expression. So what will be the ripple factor? It will be pi square by 4 because that is I naught pi by 2. So it's minus 1. So the ripple factor is becoming 1.21. Okay. Now we'll come to the percentage of the someone wants to join. Okay. I'll take maybe 10 more minutes, 10, 15 minutes. Then, yeah, there is something called the regulation. That is also important. The load regulation of the uh, rectifier. Load regulation of rectifier. So it's basically the variation of the DC output voltage with the DC load current for a given input. It's called the load regulation. So already know the IDC is I naught, so peak to peak value. Okay. Sorry, zero to peak value. It's I naught, which is also can be written as V naught pi by RF plus RL. This guy's constant. Uh, Bhaskar, you are continuously like, please unmute yourself. If you have the internet problem, you can leave also. It will be posted later. This is the regulation characteristics, and the percentage of regulation is defined as SL. You will you will come across about this thing very often because this is a very important factor for the rectification also. The no load and with the load. So VNL is basically when there is no load voltage. That is the voltage with the zero load current where RL is infinity. Okay, let me write it. is the output voltage. At a particular rated load current. So the smaller is the value of this is important actually. So you understand the smaller is the value of a cell, the better is the regulation. Is the regulation. There is something called transformer. So I will end with this particular thing. It's called the transformer utilization factor. Transformer utilization factor. Sorry, this will be transformer utilization factor, or you can simply write TUF. So it's a ratio of the DC power supplied to the load and the AC rating of transformer secondary. You have to remember this expression, then you can calculate for whatever condition will be given in the problem. This is your load resistance and divided by RMS is V naught by root 2 and current RMS by I naught by root 2, and basically your V naught equals to I naught RA plus RL. So you get a TUF to so if RF is greater than RL, then TUF becomes 2 root 2 by pi square, which is 0.287. Okay, done. So I will stop here. Probably then I can continue tomorrow. And I will check whatever yeah, you have posted now. John particularly posted in the chat box. Then yeah, we can and one more thing I would like to ask, in case in the last minute, like what happened for the week 4, I had to cancel the class. So how I will communicate to you? Is there any way? Can someone just tell me?
Email.
Email to whom?
We get email from your link of the class, so in every week.
No, that is so you know, but in case let's say I have to say ki this today's session is rescheduled to some other day or got cancelled. So to PM like NPTEL coordinator, I have to email through that you generally get, or
Another phone number or
okay, it's fine. I'll see. I'll see. Anyway, it's fine. So yeah, I'll end here. Probably you guys can leave also. Tomorrow we'll meet. Yeah, at the time. Yeah, at 3 p.m. In case I'm getting late for half an hour, I'll just write in the chat box. You can also find it from the chat. Yeah, that will be fine. You guys can leave actually. The recording will be saved after that. John Bhaskar, this guy is still there.